Okay, let's get started. So today we will keep talking about the background knowledge. Guys, be quiet. Let's get started. Okay, so first we will talk about the x86 architecture, which is most widely used architecture for laptop servers. So most of your laptops are using this architecture. Some latest Mac are using ARM, but still most of our computers are still using this architecture. And this is the architecture we use in this class. You need to remember how big data is on this architecture. Byte is obviously 8 bits. Then a word can be 2 bytes. A double word or D word is 32 bits, 4 bytes. Quad word is 64 bits, 8 bytes. Double quad word is 16 bytes. Unionist is the ordering of bytes of a value in the main memory, or other storage could be disk as well. Also, this is the ordering of data bytes during transmission. There are 2 popular Unionists. One is called a little endian. This is the one we are going to use in this class because Intel uses this endian. ARM also uses this one. Some ARM CPUs use big endian, but we're not going to use them in this class. So in little endian, value is we store the least significant byte at the lowest address, and the most significant byte at the highest address. For example, here we have 4 bytes. So 4 bytes is 1 integer, and we have 4 bytes here. So at address 0 to address 3. So obviously address 3 is a high address, and 0 is low address. So if this system is a little endian system, like the one you are given, also the horizontal system, then at address 0, the value is the least significant byte. So if this 4 bytes is one value, then you will be this value. 7, 8, 5, 6, 3, 4, 1, 2. So this is a big endian. If it's a big endian system, the order is reversed. The least significant byte has the highest address. So that's 1, 2, and 12 in text will be the highest. With most of the significant byte. Right? So this is the system we're not using. This is the system we're not using in this class. For x86, there are not many general registers. There are only 8 general registers. For this class, you need to remember those general registers. You're going to read disassembly a lot, and you will see the names very often. There are a lot of system registers in this architecture as well, but we are not going to use many of those since we are not really doing some kernel hacking. What we are doing is still user land hacking. Besides the general registers, 8 general registers, there is one special register called the E flag. As you can see, E stands for extended. Then there is flags. So obviously there was an older version of x86 which has a flag register, and it was extended to the 32-bit. That's why it's called E flag. There's another special register called the program counter or instruction pointer register, EIP. This is also 32-bit. So this register stores the address of the next instruction to be executed. Like I said, there are many other special system registers. We are not going to use them very often. The 8 general registers are EAX, EBX, ECX, EBX, ABCD, then ESI, EBI, ESP and the EBP. They are easy to remember. First is the ABCD, then source index SI, destination index DI, stack pointer, and the base pointer. So those two are very important in our class. A lot of hacking is because of those two, stack-based hacking. So you will see them a lot in the future. So in those 8 general registers, 4 of them can be accessed, half of them. For example, those EAX, you can access the AX part, which is only 16 bits, 2 bytes. You can even access the AL part or AH part, which is just 1 byte. So in the very old detailed architecture, like the old 8080 systems, those are called the 8-bit systems. The only register they have is AL, EL, CL. Then they expanded to AX, which is 16-bit. Then they expanded to 32-bit, which is EAX. And most of the computers we are using right now, they have an even bigger register, which is called RAX, which is 64 bits. Okay. So in this picture, I'm only showing the 32 bits ones. But later, we're going to see the 64 bits ones as well. So the first special register, not general one we're talking about, is this E-flags register. Basically, it records the status of the system. There are many bits, or you can say 32 bits. Not all of them are used, but some of them are not very important for us. We only care about several, which is the carry flag, parity flag, zero flag, and sign flag. We do not really use them directly, but a lot of instructions depend on those flags. So you probably heard of those in the computer organization course or assembly language course before. The very important register instruction pointer, EIP. So this is on some other architecture, this is called the program counter, or PC. For example, on ARM, the same register is called PC, program counter. It holds the address of the next instruction to be executed. So this is a picture of many other registers we have in our x86 architecture. As you can see here, we just spoke about the general registers, which are here: the EAX, EBX, EZX, EX, EBB, ESP, EBI, ESI. Those are the 8 general registers at the 32-bit version. Then you can say that this picture shows the 64-bit version. So that's why I can say EAX actually is already extended to RAX, EBX extended to RBX. And we have more registers like R8, R9, R10. So those are only available in 64-bit version of the system. Let's see what other registers are interesting here. So here you can see all the CR registers. CR stands for configuration record, maybe. So those are system registers, the operating system, the kernel will use. For example, when you do a context switch, you need to change 2 different processes, their address sets. And their address set, there is a memory map, right? The MMU will use a memory mapping table to translate the virtual address of the process to physical address. And to do that, you have to know where is that memory map table. And that memory map table address is stored in the system register CR3. Okay? So CR3 is for that purpose. So in our class, we're not really using those. Like I said, there are also PR registers. Those are for debugging. D obviously is debugging. So there are old segment registers, CX, code segment, SS, stack segment, ES, not segment, but in later system, we're not using segmenting anymore. Also, there are other registers, IDTR, which is interrupt descriptor vector register, something like that. This is a local descriptor register. So you can say also the flag, the E flag registers can be with R flags. So those registers, we're not going to use them very often. Those are the registers that I talked about. And on this side, we have even more registers, bigger registers. Some of them are not even 64-bit, pretty much bigger, to be 512 bits. Okay? So those registers are for multimedia computations, floating point computations. So we will not directly use them in our class. There is one or two examples in our class. We were debug. When you debug, you will see some instructions using those registers. You are not. We're not going to use them a lot. So all the instructions on this platform looks like this. There is an optional label and column, then another mnemonic, basically the name of the instruction. Then there could be several arguments, up to 3 arguments. So those kind of the binary level, we call those arguments operand, so 1, 2, 3. So each argument can be a constant number or an immediate value, which means the same thing, or it can be a register. It can also be a memory address. So each argument is either a source argument or destination argument. The source argument, obviously, it can be the constant, register, and memory address, but the destination can only be a register or a memory address, because you can only store something to a register or to a memory location. It doesn't really make sense if you want to store something into a constant, right? So I will show you several examples. Those are the instructions with different numbers of arguments here. The first one is HLT. Obviously, it means halt. So it stops the CPU until there is an interrupt or something. So look at the description of this instruction. You feel there is no need to have any arguments, right? So this instruction doesn't really have any argument, just the name of this instruction. Then there's another instruction, INC means increment. So increment can be, this instruction can have 2 different arguments. It can be a register or it can be a memory location. It will increase that register's value by 1 or increase the memory location value by 1. So it takes 1 argument. Then there is an add instruction which has 2 arguments. The 2 arguments can both be registers. So in this case, in the Intel syntax we're using, we're using AKD syntax, right? The AKD syntax we're using, this is the name of the instruction add. And the first one is the source register, and the second one is always the destination register. So we are adding this value to this value, right? Where you don't have instruction like IMUL. This MUL obviously is multiple multiplication. I is, I would say, integer. Then you can take up to 3 arguments, something like this. IMUL, register, and a constant. So this one, what I thought is times this one with the constant to the value back to the second register. That's how it works. So, like I said, I'm not going to talk about all the instructions one by one. Some of you are graduate students, some of you are seniors. So if you see some instruction you don't know, you just Google the name, you just Google the instruction name and the detail. 32-bit, 84 bit. Then you can find the description of those instructions. There are two types of assembly syntax for this architecture. One is the AT&T syntax. Another one is the Intel syntax. They are equivalent. We will mainly use AT&T syntax in our class. So all my slides, I'm using AT&T syntax. In the homework, we're also using this syntax. But you should know that there's also Intel syntax, and you should be able to tell their difference. So if you say a piece of code, a disassembly code, which is in Intel syntax, you will not get confused. So some of the tools we are using, they can generate both Intel and AT&T syntax, so you can choose. So all the instructions on this architecture, they generally fall into three categories, especially at the username level. The instructions fall into three categories. First one is data movement. We just move data from one memory location to the register, from register to another register, or from register to memory to some memory location. Or arithmetic logic instructions. They do the computation. They add something, multiply something, divide something from something, so those instructions. Then there are control flow instructions. They control how the program execute the next instruction. In the syntax we are using, for all the registers, we have a percentage sign in front of the register. So when you say percentage EAX, then means that is a register. So you can access all kinds of registers here. The memory location, we are using the round brackets to indicate this term here means this is the memory location we're talking about, and the address of this memory is at EAX. So when you say something like this, EAX, we're talking about the content of the register EAX. When you say something like round brackets percentage EAX means EAX stores the memory address, and we want to know on the memory address what is the content. So you could also something like this. This actually means EAX times 1 plus EAX, and that's memory location that we have. We have more examples in this. The constants can be different size as well, 8 to 32 bits. Give you several more examples so we can understand those instructions. So all those instructions here are moving instructions. So in this syntax, so when you see this percentage sign with some register name, you know this is AT&T syntax. Okay, the Intel syntax doesn't have this percentage sign. The Intel syntax doesn't use round brackets. It uses the square brackets actually. So this instruction here read as move from the first operand to the second operand. And the first operand argument here is we have the round brackets. This is the memory location. The memory location is specified in EBX. So basically, we are moving 4 bytes from the memory address specified in EBX, move that value to the register EAX. So this is different from directly moving EBX, EAX. That is moving from register to register. This one is moving from memory to register. So the second one, so this is just the syntax. Basically, we're moving 4 bytes. So everything here we're moving 4 bytes. So this is a 32-bit machine. We're moving the memory address ESI -4. Okay, this is just a syntax. So you put the -4 out of the round bracket. You need to move that memory location, the value, to EAX. Then this one is This one we're not using ECX. Instead, we're using CL. So CL is one byte. So this instruction is not ambiguous. We know this is only moving 1 byte because the source argument is only 1 byte. So the destination is ESI plus EAX times 1. Okay, so you are moving 1 byte to the memory. The memory location is this. Okay? So you may find this a little bit weird, but think about if you are, this is more like a array operation. Okay? If you are doing some array operation a lot of times, this is what your code will look like. The first one is kind of like the base of the array. This one is a constant. That's like the size of each item in the array. And then EAX is kind of the index of the array. Right? So if you can do a loop here and you change the EAX, then you are moving a lot of data to that array. That's why we have a weird instruction like this. Okay, the next one is actually similar. It's just that we're moving from memory to EX. The base address is ESI. The index is EEX in this case, and the size of each item is 4 bytes in this case. We're moving 4 bytes from the memory 4 times EEX plus ESI to EEX. So those are several moving instructions. So in general, the intended size of those moving instructions usually they're not ambiguous, but sometimes it could be. I have several examples here. We move the constant value to, also in this syntax, all the constants, you have to use a dollar sign, which is related to constant. So this one, we're moving the value to the memory location, which is specified by EDX. So this instruction is a little bit confusing, right? Because you can move 1 byte, which you are moving 1 byte, which is 2. Or you can move, this could be 2 bytes. The first byte is at this location. Well, the least significant is 2, but the most significant is 0. You could mean that, right? It also could mean 4 bytes. That's why this instruction is a little bit confusing, ambiguous. That's why you may say instructions that explicitly say how much data they are actually moving. So that's why I say here, this is move, the E is byte. Okay, byte is one byte. So there is W, that is a word, which is 2 bytes. Or there is L, which is long, which is 4 bytes. So that's why this instruction is ambiguous. If something you want to move data like this to memory, you are more likely to say like one of those instructions which explicitly specify the data item size. Okay, so those are the examples of moving instructions. The moving instruction can move from register to register, register to memory, memory to register, or move a constant to register, move a constant to a memory location. Then we have another data movement instruction called push. This is a very important instruction in our class. We will talk about this a lot for almost a month. It's based on problems with those instructions. So the push instruction places the argument onto the top of the hardware supported stack in the memory. Hardware supported stack means the location of the stack is specified by the register ESP. That's why it's hardware supported. So the push instruction will first decrement ESP by 4. This is a 32-bit version, so by 4, it's 64-bit version by 8. Then place the argument at the location that ESP points to. You can push a register value there. You can push a constant. You can also push a memory value there. For example, if we do a push percentage EAX means we're copying the value of EAX to the stack. Stack is part of the memory, the DRAM. We're actually decreasing ESP first, then we copy to the stack. The stack goes down. Since there is push, obviously there is also pop. Pop also take one argument, and that argument is the register or memory location that receive to store what you are popping. So it's always pop from the same place, which is the top of the stack. And top of the stack is always specified by ESP. The ESP points to the top of stack. So the pop instruction will first move the data from top of the stack to whatever you gave. It could be a register, it could be a memory location, then increments that ESP by 4. For example, we can do a pop percentage EDI, then we're popping the top element of the stack into EDI. Also, the byproduct here is the ESP is moved, which is not explicitly specified in this syntax. In the syntax, you do not say ESP, you only say pop EDI. But the byproduct of this instruction is ESP is changed. Same as push. When you do push, the ESP is also changed. Another useful instruction is called load effective address. Do not take the name of the instruction literally because this instruction actually is used for quick calculation. Here is an example. Instruction is always used like this, okay? The first argument is a memory location. The second argument is a register. So we already know what this is, right? This is ESI times 8 plus EDX. And that means the address on the DRAM. And we are loading that address to EDX. Okay. So basically, this instruction does is EDX is assigned with a new value, which is EDX plus ESI times 8. It actually has nothing to do with whatever is at that memory location. It's not reading the memory. That's why this instruction is a little bit confusing. Even though it has this wrong brackets, it's not really reading from the memory. Any questions so far? Yeah. This one? Just remember this one as EDI assign the value ESI times 8 plus EDX to EDI. Just remember that one. Now remember the name of it. So, for example, you may ask, why do we need an instruction to do this? Because there is no other instruction to do that. If you want to move the value I talked about, this value to EDI without using this instruction, you will use at least two instructions. The first instruction is you will use multiply instruction, multiply 8 with this, right? Then you will use another add instruction, add this one. So with this instruction, we do that in a single step. Those are some examples of the arithmetic and logic instructions. The first one is addition. Like I said, the second argument here is the destination. So it doesn't make sense if we swap those two. Okay. If we do percentage EAX and the $10, that doesn't make sense because 10 cannot be a destination, right? However, in Intel syntax, they are actually swapped. The first one is the destination. The second one is the source. So this instruction will just add 10 to EAX. The second instruction here is add 10 to the memory, which is specified by EAX. This is a little bit ambiguous. That's why we specified with P. We're just touching one byte here. Another one is a subtract SUB. So we can subtract AX from AL. So So basically AL is set to AL minus H in this case. We can also subtract a constant value from a register. D say is increment. That's one. There is multiply. There is shift right. So this one is shift EBX right for CL bit. So if CL is 1, then we're shifting EBX right 1 bit. So it's kind of like dividing 2. If we should, if CL is 2, then we're dividing by 4. Those are the arithmetic instructions. Then most importantly is the control flow instructions. The first one is called jump. It transfers the program control flow to the instruction at the memory location indicated by the argument. So you can jump to a label, and that is called a direct jump. You can also jump to a register, which is called an indirect jump. From program analysis point of view, if you do a static program analysis, for example, compiler does static program analysis. The static analysis does not always know the target of the register, because only runtime you know the value in the register. Or for those labels, the address can always be calculated. That's why this is called a direct jump. This is called an indirect jump. The same thing applies to the call instruction. There is direct call instruction and the indirect call instruction. For example, jump begin. The begin is not a register. It's not a memory location. So obviously it's a label. So there is a label called begin, and we're jumping to that place. There are direct jumps, indirect jumps, and there are also conditional jumps. You don't need to remember all those, but they're not hard to remember anyway. So you can see all those instructions, they are called the conditional jump instructions. The first one, E means equal. It will jump to this location. It could be a label, it could be a register. Jump to this location when the previous calculation shows those two values are equal, or NE not equal, 0, G greater or equal, less than or equal. So for example, this is two instructions. First, there's a compare. We're comparing EAX and EBX. After we're comparing those values, we will decide where do we jump. So this is a conditional jump. So this compare instruction, what it does is it's actually a subtraction. It will subtract EBX from EAX. So after the subtraction, the E flags will be updated. The E flag has several bits, right? There is 0 bits, parity bits. If the value is 0, then the 0 bit will be set. Then we can use this jump less than equal instruction to check that 0 bit. If the 0 bit shows is set, it probably means they are equal. So this jump will be taken. This conditional jump will be taken. Go ahead. Where does it jump to? It's the same as all other jump instructions. It can jump to either to a label or a register. Yeah. So when I say down here, you might not know a little bit about the compare instruction. Like I said, it subtracts the first argument from the second argument. It can be registers, memory locations, also constant. So this is another example. We take the value out of the memory address EBX. We subtract 10 from it. Then based on the value, we decide if we want to jump to this label location called loop. Okay, one of the most instructions we use in this class. This is the subroutine call instruction. This instruction has several steps. It first pushes the current code location onto the stack in the memory. Then it performs a unconditional jump to the location indicated by the label or the register. Okay, so this is not a simple jump instruction, which we only directly jump. We actually saving where we are from to the stack. Since there is a call, then there is also another instruction called return. And a lot of our tags are based on this instruction to return. The return instruction implements a subroutine return mechanism. It pops the code location of the stack to the program counter. It pops whatever ESP points to, the register ESP points to the EIP. So if you control what it pops, then you can control where the program will go to. Okay, the syntax of this is very simple, just a return. There is no need to have any argument because implicitly it already says I'm popping from the top of the stack. Okay. An important concept here is a stack. The runtime stack supports procedure calls and the passing of arguments or parameters between different procedures or functions. The stack is located in the main memory, usually DRAM. Yeah.
Register and what? It's the same way for register. No. Register and pointer are not the same. Register, they are some small storage inside the CPU. What you put in the register is an address. You use that as an address. That means it's kind of like in basic programming, that's kind of like a pointer to somewhere in the memory. So what you point to is something another way. So what you point to could be code, could be data, right? So when you point to the code, you put a code point. Otherwise, you put a data point. That address is stored in the content is memory.
So in the architecture we're using, the stack goes down from high address to low address. Intel ARM, most architecture are doing that way, but some architecture goes up. ARM actually you can choose. You can choose to go up or down. Since the architecture we're using, the stack goes down, which means when we push something to the stack, the ESP, the value will be decremented. So the stack goes down like this. If we pop something, ESP, the value will increment it. You will see those three instructions a lot. Usually, those are called the prologue of a function. So at the beginning of the function, you will see those a lot. Those three instructions. The first one is push EBP, means the EBP value will be pushed on the stack. Then move ESP to EBP. Remember that this push one will change ESP. Then you will store the current ESP value to EBP, then subtract something from the ESP. You don't have to fully understand this. We're talking about this again next week. But those three instructions, because they occur so often in Intel, they introduce a new instruction called enter. So this enter instruction is equivalent to this. So sometimes you will say the enter instruction. Since there is enter, you can imagine Intel will also introduce leave. Okay, so leave is the operated one. It will move EBP to ESP, you install EBP. Okay. You do not have to fully understand how this works now. We'll talk about that next week. Okay, we already talked about the 32-bit version. Now we move to the 64-bit version a little bit. We already see this figure. You can see everything here. This figure shows all the registers on this Intel architecture from the very early 88, CPU. When there 82, 86 CPU. Right? So when there was Clinton CPUs, I don't even know what the CPU name we're using right now. So what we're using is 64-bit. So, but they are always backward compatible. That's why you can still access AL, BL, those legacy registers. Okay, then we are going to use this example to show how 64-bit program are different from the 32-bit program. We actually did this on last class, so I didn't show you the results here. So you can see we have the main function. This is the program with the main function. There are two local variables. Long A and the long B. Long means this is 64 bits. This variable is 64 bits. However, our machine will be 32 bits, right? When the machine is 32 bits, means this variable we cannot use a single register for it. We have to use two registers, right? So we check if the argument is 3. If it's not, we'll find out how to use the function. Basically, we are going to add two numbers together. Then we print off the size of the llama. No matter which version you are using, 32-bit or 64-bit, the size of this should always be 8 bytes. Okay. So llama is consistent at the secret level, 8 bytes. So we get those two values, we add them together. Okay. So this, I use this weird function here because I want to show you guys pointer is basically adding those together. The first one I'm using the address. Second one is actually using value passing. The first one is on the reference. So we just add them together. So if we go to our cloud server, so this is a challenge you can run to run this one. If you run this one, let's see what we have here. Which one do we have? We have the source code. Just say this folder. You can say the source code main.c, the make file. The make file could be old one, so it may not working. Let me check if it works. So kind of the make file. Oh yeah, I think it should work. Okay, so you can just do a make. You can do a make LADD. Then we get the 32 version of this program. We do a LDD 64, then get the 64. There's a warning, but doesn't really matter. So if we run both programs, the first one we add the two big number together. We get the size of long is 8. And added it together. The 64-bit version, we do it, get the same value. Okay, there's no errors. However, if we disassemble this, we can tell they're different. We're going to use a tool, the simple tool objdump -d to disassemble this. So this is the program we use a lot in this class. A simple program, non-line. Not fancy at all. They're all fancy to convert, so we rely on simple tools. So simple tools shows you what exactly is going on. We rely on those fancy algorithms. So when we do this, we can find it can disassemble all the functions in this program. And we look for the function LADD here. Can everyone at back can see it? Okay, good. So this is the 32-bit version of the program. And you can see, like I said last class, let's just ignore the first instruction. It's a security feature, not very important for now. For most machines, this instruction was just like a load operation. No, we're not doing anything. Then what it does, it will move ESP. Okay, let's try to understand this. There's one way to learn. We're moving 4 bytes from ESP plus 4, that location, to EAX. Then we're moving EAX plus 4 to EDX. We have this weird thing. You can see that. This is a pointer. Now this is another pointer, and this is a E reference plus. That's because in our code, we're using address, the different E reference address, right? Then we move that value as that memory to EX. So we get the first, maybe that's A, or maybe that's, yeah, I think that's A. And we get a value A. Then we add value A to value A is already EX. We add it to value B, which is at ESP plus states. Okay. Then we add another carry here. Add another in here EX. Why am I doing the EX? Oh, yeah, this is interesting. Why we're doing EX? Remember, the variable we're adding here is 64 bits. EX is only 32 bits. So the value is actually represented in 2 registers, which is EAX and EDX. Okay. Together, that's our value. So we're using 2 instructions, like add, another one add with carry. Okay. So this one refers to the status register, the carry learning returns. So this is the 32-bit version of the program. It has, let's go the first one. This here has 6 instructions. So if we look at the 64-bit version of the same program, you just saw that. I compiled it from the same source code. We look for the same program here. It's actually only 3 instructions. Okay. The first instruction, the second one, security one, you know that. The last one is not really instruction because we already returned. Okay. This is not really instruction. That's garbage, and the tool we're using doesn't know we should stop here. So we keep interpreting this as instruction. So there are only 3 instructions. And we're just using RAX, RDI, RSI. And those are 64-bit registers. We can represent those control services. 3 instructions. So this is one of the reasons why our CPUs are getting faster and faster. 10 years ago, the CPU has to run 6 instructions at a lower frequency. Now we are just the same thing. We're only using 3 instructions at a much higher frequency. So in the homework, you are going to compile this. You can use my makefile there, or you can just type everything here. It's better if you just type for you to better understand what's going on. Okay, then we talk the next piece of background knowledge, which is Linux's file permissions. So each file and directory in Linux has 3 user-based permission groups. One is called owner, group, or others. A user is the owner of the file. By default, whoever creates the file becomes the owner, but you can change the owner. A group can have multiple users, and other users on the system which do not belong to the group or the user are called the others. Then for each file, there are three different permissions. One is read permission, write permission, and execute permission. So if you do ls-l in a folder, you can see all the files in that folder, and it will show you something like this. First column here tells you what this file is. Is it a real file or is it a directory? If it's just an item, means this is a file. If it's a PP, means this is a directory. Then after that, there are 9 columns. Those 9 columns use the permissions for different groups. The first 3 shows the permission for the user, the owner, then the permission for the group of the owner, and for everyone else. Let's say we have a PDF file. Let's say the PDF file is not a directory, there's no me. If I'm the owner, then I'm the owner, I can read and write to this file. However, I cannot run this file of an executive, right? I don't have that permission. Of course, this is my file, I can change the permission. Anyone in my group, they can also read and write, but cannot execute. Everyone else in the system, they can only read, they cannot write. Okay? So this is called the access control for Linux works. There's another example, foo.txt. I can read and write, but everyone in the group, they can only read, they cannot write. Okay? So it also shows link count of that. Also, who are the owner of those files and who are the groups, and the file size. Last time this file was modified, the name of the file. So if we do this on our server, just do it on this folder, ls-al. We can see those other files. First, there is a current directory. This directory called is the current directory. Top is the parent directory. It's so the current directory owner is CPS. The parent directory owner is root. They have different permissions, and we just created those 2 files, right? We compile those 2 files. So those 2 files belong to us. We are the owner. We can read, write, and execute. Okay. Everyone else in this system can also execute, and we get access to everyone else. But they do not have the permission to write. The main goal says that the source code, you cannot execute source code. So there's no access, just the relay. So after that, we can talk about what are set UID programs. So the file permissions we just talked about guard who can access which file on the file system. The file system is static. It's usually on the disk. However, an executable, or we can call it a program, is usually stored as a file on the file system. However, when a program is loaded into the memory, it becomes alive, and we call it a process, right? So each process in Linux has 3 user IDs associated with it. So all of this I talked about today here. I will also give you some readings to do, okay? It's hard to remember what's going on here, so that's why I'll give you some readings. It's not like you have to memorize it, you just need to understand it. There are 3 user IDs associated with each process. The first one is called a real UID, RUID. So this is the UID of the user or process that created this process. Then there is something called the effective UID. This is the UID used to evaluate the privilege of the current process. Most of the cases, real UID, the effective UID is the same as the real UID. So whoever creates the program is assigned to the effective UID. Then there is a saved UID, which is not that important in our case. Okay, so for most programs, so like what we have here, we have in this folder we have 2 programs. Okay, those are not set UID programs. If they are not set UID programs, when those programs are executed, their effective UID is the same as the real UID. The real UID is the owner. Okay, so the real UID is whoever runs the program. Okay, so for example, here is this program LN. This program belongs to CPF, but it is executable by anyone. Right? There could be anyone executing this program. So the effective UID of this program, the process, will be anyone. It will not be CPF. Right? However, for set UID programs, there are some programs that are called the set UID programs. For set UID programs, the effective UID is not whoever runs that program. It is always the owner of the program. Okay. So this is a very useful feature for Linux. Let's say this is my local computer actually. My local computer is just a regular I list all the programs under my root bin folder. Or you can say there are so many programs. Sorry. So those are different programs, and you can see there are several. SU, switch user, mount. Those programs are you can see here. There is an X. Everyone else has X in this active. Right? So those 2, they do not have X, they have S. Here, S. S means this program is a set UID program. So if whoever, for example, I'm running, I run the program cat. When I run the program cat, even though cat belongs to root. When I run cat, the effective UID of cat is there, it's not root. However, those 2 programs, those are special programs, security related. They need a privilege to run. So when you run those programs, the effective UID of the program is root. It's not them. Okay. So our whole call system is based on this simple Linux feature. As you can see here, we go back to this folder. This is not the right challenge to show you. And we'll use the read secret challenge to show you. Okay. So this is the read secret challenge, and this is the root folder for that challenge. And then we have a flag here, right? The flag belongs to root. The permission it has is only one item. Only root can read this flag. No one else can do it. So now I log in as CPF. So if I do a cat is not a set UID program. When cat on this one, my effective ID will be CPF. And system will say CPF doesn't have the permission to read the flag because CPF belongs to here. Others do not have any permission. Right? However, we have another program is ID secret, read secret. This is a set UID program. It has S. This set UID program belongs to root. When no matter who executes run this program, the effective user ID of this program will be root. And root has a permission to read this flag. Okay? So all our challenges are designed as set UID programs, but they do not necessarily directly read the flag.
they are designed as set UID programs, and they have bots. But you have to exploit those bots somehow to read the content of that. Because it's a set UID. No. Because this program, anyone can run. See? Yeah. Anyone can run. Only that program, you cannot receive your own. Only that program affected your ID. Because if you look at your own program, other people yes, all that.
So obviously, if we do a pant flag, it will not work. Permission denied because the user is a CTF. But if we do a read secret, oops, read secret, oh, the name is week 1 something. Yeah, this one, and it will show you the flag.
We first should print off the effective UID 0, which is root, and the UID is CTF. So this is number. This is the name. Who can run the program is defined by who can run the program, nothing program is a set program. It's determined by the fire permission for this program. It's determined by, for example, this is a program. It's determined by those 9 permissions. Yeah, most likely you will be out. So the SU can be executed by anyone.
So we just do ls bin su. Okay, so you will expect for everyone they have the x there, right? Yeah, you can see everyone has x. Okay, and this is a oh, this one somehow is not. Maybe this one somehow is not a SETUID program. Probably because everything we run is in a Docker instance actually. Yeah. Okay, I think we still have something to cover. Yeah, this one contains S. This is my local box. That one, this one is actually a Docker image. So means here you cannot really do SU. We do not really allow you to do that. Yeah. The source code of that read secret is very simple. Main function, we first call the system call get UID to know who is the user ID. This structured password is just to get a string who is the user's name. But this one we're only give you integer, and we need to get the name of that user. From there, we'll also get the effective user ID. That's another system call. So those two are well, typically at this level, these are C library calls. But those C library calls eventually are mapped to system calls. Then we just print out that. And that's it. The print out flag is very simple. Just open the flag file, read the content, print out. That's it. So the code, this code, so this program is SETUID or not, has nothing to do with the source code. Okay. You have to change the program of the set UID program in the terminal. So after we compile it, we need to set this set UID program. This one we will skip. This one, let's see. Okay. Let's see if we have time to talk about this. Oh, we still have still have 15 minutes. Okay, we can go ahead and talk about. Here is just a simple background knowledge of L files. We will spend almost the whole class to talk about L files next week, actually. Okay, so L files are the executable format in the Linux or Unix operating systems. So correspondingly, Windows, they have their PE format. This is a format, and this is a standard for different executable files. The first is standalone executable files, object files, shared libraries, even core dumps. When your program crashes, the system can generate a core dump. So all those programs will have the machine code. Okay, so you can see different extensions associated with L file. It doesn't really matter because Linux doesn't rely on extensions. Windows rely on that, but Linux doesn't. So there are different ones. For example, AXF usually for embedded systems, bin usually for the battery, L.O, KO means kernel module, SO usually is a shared library. This is a dynamic shared library. Also, .A is a static shared library. So all those L files, they have data and a program. Those L files, they describe how the program should be loaded, also containing metadata describe the other components. We can use a file. We have tried this multiple times. A file can tell you what the file is based on the header. Okay, so if you want to do a file on this one, it can tell us this is a 64-bit version L file, and then this is a standalone program. This part we will skip. We will talk about all those next week. Several tools we will use in our class. You can use a compiler like GCC to compile an L file. You can use tools like readl to pass the header. We have been using object dump several times. It can disassemble the source code, the binary code in the program. We can use NM. We can quickly do that to say if there are symbols in those files. So let's do an NM, and we do a week one this. It can show us all the symbols in this file and their address. For example, there should be a symbol called the what's the name of that function? Print secret something. Should be, so for example, F-read, F-open, we use those. Okay, I don't find that, probably because they are statically linked. So those symbols, or that symbol is not clear anymore. Yeah, there is a start we can see, but we do not see that one. Oh, here, print flag, that's a symbol. Okay, T means this is code. U means this is actually not real code. This is undefined because those are dynamically linked library. So right now we don't know their address. Only runtime, those addresses will be filled in by the loader. Okay. There's other tool like OBJ copy. You will use a little bit in our share code example. In our share code example, you're going to write some share code, compile into L. Then you will use OBJ copy to only copy the code part, the machine instructions out. There is a strict to remove those symbol informations. So, for example, let's see this program. Do we have permission to do this? So we cannot, no, we don't have permission to do this. Okay, then I will show you something next week. A little bit about the memory map of a Linux process. So Linux obviously is a multitasking operating system. You can run many processes at the same time. And each process is a 32-bit version. Each process have its own virtual address space, which is 4 GB. Because it's 32-bit, so it's 4 GB memory. And each process have their own. And those virtual addresses are mapped to physical address by page tables. And page tables are maintained by the operating system. Also, operating system will use the MMU, a memory management unit, which is part of the CPU to do that translation. So this is an example memory map. Things have been changing a lot. Because now for security reasons, we randomize everything. But 10 years ago, this is what the memory looks like for each process. First, this is at one time. This is not in any system. We first have the code, and the code is from the F1. This is code where we have data sections and global rows. They will be copied in memory. Then there are DSS segments. DSS, I don't remember what it stands for anymore, but this is a segment for uninitialized global variables. So in the program, you can have a global variable, but you didn't initialize it with anything. So the loader doesn't have to copy anything from the F to the memory. But still, at one time, those variables, they have address, right? That's good when we are here, okay? Then there is something called D. Goes from no address to high address. So it's what you get from something like malloc. When you don't need that, you use free. Okay? So it's not really managed by the kernel. It's the user has to manage the heap. The kernel belongs to the heap management at the full bytes level. The kernel doesn't do that. The kernel will be like a pig set. Okay? So that's why at the kernel there are system calls like arcade to set the under the heap. Most of these operations are included. Then there will be some memory management segments. So those are the dynamic libraries and also static libraries. When you write a C program, you will call a lot of other functions. Some of them are sitting standard library functions, and they will be mapped to here. Okay? Then there will be stack, and stack goes up. Stack is used to store temporary data, such like local variables. See how that works. Then the higher one is directly mapped to the kernel phase, which was programmed. Okay. So this is a view, but like I said, most of the things are not at fixed address anymore. So in this translator, you will see what? Not pointer. Okay, we can skip this one. Okay, let's do one more demo. So this is a simple program translating. So that one has basically waiting to type the thing like not type anything, the word stay there. So what we can do is we can use this program to show the memory map. We go to challenges, we go to the 32-bit version, we run it. Let's go ahead and use Tmux here. Okay, we can actually run two terminals here. Okay, we have two terminals here. We are going to run have this program. So we're going to run this program here. Week 1. Okay, so this program is running in this terminal. We switch to this terminal and try to find PS here. Oh, this is the same thing. Okay, so we can see, make this a little bit smaller. So from PS, we can say this program is running. Then this is where the PID 59. So we can do a cat of the memory map using, let's use, I don't know if we have the PMap tool, let's see. I don't know if we install the PMap here. 59. Instead of the PMap, let's do. Ooh, this one we probably do not have the permission to do that because this is in Docker. Yeah, we don't have the permission to do this. Okay, instead I will do this in my local machine to show you. Which one is it? Process map. Okay. Now with PS, X. Too many things here. We do a grep, PM. Then we have it here. This is PID. So we can do a PMap. This one.
Yeah, I couldn't show the demo on the server because we don't have the permission to do that. We don't have the permission to review any other programs. Okay. So this is on my local computer. On the right-hand side, we're showing the wrong single program. I mentioned the program where it's active. On the left-hand side, we have the memory map of this program. And so I will just quickly show you the sections. There's a stack section, and there is the location of the stack section. Those are the standard city libraries. So here are the standard city libraries. Those different memory locations. And you can show their different permissions, read and execute. The stack on is the active table, so there is no X. Then those are the loaders. The loaders are the loader program, so they're also mapped to the same address 6. And there is a D. So those ones are the source code, not source code, the binary code of the program itself. That's like module and VPN. So some of this one. Clearly, this is the control part because of that. The other part, there's no X, there's already only analog and like that. So this one is read and write, so this could be global variables. So that's what the memory map looks like.
The 34-bit system would be similar. If we run the same program, 64-bit, we get similar things. Okay, we don't have time to cover system call, so we will talk about next month. Okay, see you guys next week. Any questions? Any questions from the folks online? No questions? Okay, then you are dismissed. Stop recording and under the